All right, let's get started. I'm Sandhya. I work for a small consulting company called Nthought, and we'll be talking about NumPy, an introduction to NumPy. I just want to first make sure that everybody has had a chance to install the environment and is able to basically do a Python check-in.py and you get the smiley face. Let me know if you haven't gotten here yet. We'll have a few minutes, and I have two helpers here, Matt and Nathan. Sorry, Daniel, and they'll be able to help you to set up the environment. Did everybody, if you have gotten the smiley face, please raise your hand. Okay, we have at least a couple of them who are still setting up their environment. Anybody, any problems setting up the environment? Okay. He's yeah. And if you have already set up the environment, um, go to your terminal and do a conda activate NumPy tutorial. And then Jupyter, either notebook or lab. Database is fine. So if you open it up in the directory, you'll see all the files in there. I'll mostly be working through the slides here. There is a PDF here, which is basically all the slides, and pretty much I'll be covering this material. And there are exercises and stuff in here. But I would suggest you start a blank notebook, and we can get started from there. All right. Since this is a tutorial, I'll be working through the material, and I would suggest you open up either an IPython terminal or a Jupyter notebook and work through the examples, and we can talk about it. And if you have any questions, please feel free to interrupt or raise your hand. There is also a Slack channel for the conference. It's called Tutorial Introduction to Numerical Computing with NumPy. I won't be monitoring this Slack channel, but maybe somebody else in the room will be able to help you or answer your questions. It's in the SciPy 2023 organization. All right. Anybody? Yeah. Actually, if you do not have Git, so I've just sent this thing on the Slack, the path on the Slack channel. So if you do not have Git, you can just click on the zip file and just download it and unzip it. So you can try this. Can you go to that link and just download? It's in the Slack channel, the path. Yeah, just download the zip and unzip it. You should have everything. Yeah. All right. So let's get started. If you still have any installation issues, Matt or Daniel will be able to help you. So welcome and thank you for coming to Introduction to Numerical Computing with NumPy. Um, so NumPy, we are here at this, SciPy conference. Everybody is talking about all the fancy SciPy packages that people have come up with, people are using. And for most of them, a fundamental part of that is the NumPy library. It forms the basis of the scientific Python ecosystem. And pretty much any library that you try to use SciPy or Matplotlib or Pandas, everything is built on NumPy. And we will talk about the reasons for it and also like how to use it. One of you see the C Python here, and then there is Fortran and the C programming language. Okay, no, let's not. So the real power of NumPy comes because you can have a lot of mathematical operations are based on arrays, and uh, the operations in Python, in pure Python, as the arrays get bigger, are kind of slower. They're inefficient. So what NumPy and the other libraries in the scientific Python ecosystem do is to actually implement it in a very efficient manner in either Fortran or mostly in the C programming language. And that's what we leverage by using these libraries. We have a nice, convenient Pythonic interface, and but we are actually getting the speed and the power of C without like dealing with the actual code directly. So first things first, it's a convention is to import NumPy as NP. Let me. Okay, can you see in the back? Is it clear in the back? Yeah. Okay. Okay. Does anybody know how to get rid of the top part of your top bar? That's fine. Pardon me? FN. Yeah. Okay, that's fine then. A little bit of less real estate, but that's fine. So, how many of you have been using Python? All of you have used Python. You have used Python for more than a year. Okay. All right. How many of you are familiar with NumPy? Have used in some context or the other, like either in scikit-learn or image processing or some stuff like that? Okay. Little bit of familiarity. Okay. So first, I would like to talk about why we need NumPy and how it relates to what we already know in Python. So in Python, we have lists, right? Very simple. And let's say I have two lists. Now, if I want to add two lists, what does this do? This concatenates it. This is pure Python. I have not started using NumPy yet. It concatenates both of them. But for numerical operations, that doesn't, in most contexts, this doesn't make sense. We need actual math happening on it. And NumPy has a rich set of functions which implements this for us. So if I have to actually do element wise adding in Python, right, I need to write my own loops for I and A, and then this, sorry. So I'm taking the first element in A, the first element in B, and then adding them together and actually putting it in a list. This is our familiar Python. We just have a loop, take each element, one element from here, one element from here, and then add them together. Have you been set up? Have you been set up? Are you able to run it? Sure. Okay, great, thanks. So this, we have to write our own loop. Let's say if we say create numpy arrays. The syntax for that is numpy.array, and we the simplest case, we just give a list here. So now we create a numpy array for both of them, and I can directly say add them together. And this is much more straightforward expression rather than having your loop. Couple of things to note here. Maybe this is addition and this is just single dimension. So your for loop is not, it's not too bad. I know it's just a couple of lines of code. But as we have more and more complex operations, implementing your own is messy, error prone. So it's great to take advantage of a library. And the other thing is NumPy is much more efficient and performant than doing our own operations in Python. So that's one motivation. And let me also show you the NumPy documentation. It's at numpy.org, and documentation. It's pretty nice, I'd say. There is getting started for the absolute beginner. User guide, I like the user guide because it gives like overall picture of certain concepts. And there is also the API reference, which is basically all the functions and all kinds of stuff that's uh, going on here. So you have lots more what do you call it? Details here. But I would get started with the user guide. So let's say what this type is basically, this is a Python function to tell you what kind of data that is, and the data type for the array is ND array. ND array stands for n dimensional array. So when we have a NumPy array, it also comes with certain useful methods and attributes on it. And I can, few useful things is array.size, which is the number of elements in there, array.shape. Array.shape gives me a tuple. And since this is only a single dimensional array, there is only one element here. N dim, number of dimensions, it's a single dimensional. So in the shape tuple, we only have one single number. If it's a two-dimensional array, you'll have two numbers in here, and stuff like that. So one helpful thing is once you type in the array, you can have a dot and then do a shift tab. Shift tab in Jupyter Lab. This is for Jupyter Lab, Jupyter Notebook or Jupyter Lab. It gives the docstring document here, so you can see more details. And basically, since I just did it on the array itself, it said, okay, this is of type ND array, and it's giving me how it shows it, and it gives me some certain, like whatever the documentation that is, official documentation that is. I can close that. Another way of, let's say I want, dot, and then if I just do a tab, no, not shift. So I just typed n and did a tab that gives me all the attributes and the functions that are available on that. So this is independent of NumPy. This is more of a Jupyter feature where you can get some helpful information, and I can select one of them, do a question mark. Edit an error. Oh, truth value. Why is it even looking? Array underscore a, and then a question mark. The question mark also gives the docstring, the documentation for it. So different ways of getting help for whatever you would like to do. So tab, shift tab, these give some like information for you to look at, which will help you like with whatever you are trying to do. All right. And NumPy also comes with a rich set of mathematical functions, np dot np dot sign plus. So I can take sine and cosine. I can take absolute values, percent absolute. Uh, so notice that the function is applied on every element of the array, and this is the advantage again we get over Python. You don't have to write your loop, go through each element by yourself, and actually do it all by yourself. And most of the standard mathematical operators are available. Like you can just multiply it with a number. You can divide it. You can take the denominator. That's a modulo operator. It takes it divides every element by 3 and gives you the remainder of the result. So now I just mentioned that NumPy arrays are good for us for array operations because it's much more efficient storage. It's much faster because it's implemented in C. This also gives us some constraints that we need to be aware of. For example, like a list, right? Let's say my Python list, C. I can mix up different things. I can have a list of numbers. I can have a list of characters. I can have other lists in here. It really doesn't matter. I can mix and match things. Things will work. And I this is a Python list. Append. I can just create it once and then append it later. So there is a lot of flexibility in the Python lists, but one of the constraints that comes with using NumPy is that you have to have all the elements of a single type. So for example, we created our array A and array B, right? So there is something called D type, array, not array A dot D type. D type stands for data type. So it tells you what kind of data that is in there. So this is of int64 type. There are multiple types in the NumPy library. Int64 is common. I think Windows will have a slightly different default. I heard. I haven't used Windows. Yes. Yes, yeah. Windows has a different default. Yeah. See, that's confirmation. So Mac and I think Linux kind of systems give int64 as the default. So for example, right, if array, now if I try to create another array, C and p dot array, and I have 1.0, 3.4, 5.6. So these are my floating point numbers, which give me float 64. So earlier, when I created the array, I just had 1, 2, 3, 4. So NumPy, when creating the array, it saw that these are all integers. I'll just use the default of an integer. Now it sees that there is Uh, there are floating point numbers. Floating point numbers are basically not whole numbers or not integers. And it says, okay, fine, let's make them as float. This can be used almost like a list. So array underscore a, we have 3 elements here. So I can pull out each one of them. The indexing starts at 0. Um, in Python, all indexing starts from 0. So array underscore. So you have the 0th element, the first element, the second element, array underscore 1, underscore a of 2. And now what will happen if I say array underscore a of 3? Because here in my array A, this is the 0th element, this is the first element, this is the second element, there is no third element. So if I say array of 3, which is beyond my array, it's going to give me an error. So this index error is basically saying, hey, you've gone too far. You know. Now, in a regular Python list, we can just append to a list. Here, we cannot do that. Once we create an array, it's done. You can change the existing elements, but we cannot add. If we are adding, it has to be a new array. Now, so I have array here, right? So I can just index, and just like a regular Python list, I can change it. I can change the elements. Now, I mentioned a little this array underscore a dot d, right? It's an integer array. Now, if I try to change one of the elements to a floating point value, what happens? It is forced to be an integer. So you will, in this particular case, it's taking the 5.4 and it's saying you be an integer, and that's it. Now we created array underscore c, I think. Yeah, we created array underscore c, which is of type floating points. Now if I change one of these elements, let's say 1, 2, 88. Okay, this is an integer value, but when I type it out, it's actually being stored as a floating point value. So the type is forced. It's called coercion. It's coerced into the right type. So when you're creating the array, the data is of a certain type, and if you add any more data, it's going to coerce to it. Now, here this 88 is an integer. It can be made a floating point. It's okay, fine. But what if I try to make it a character? It's not going to like it. Okay, it's basically saying a is a string. I can, if this array is of type float, I cannot convert it. So error out. My array C is still what it is. You can also see how much, space it is, each element is taking by using item size. It's 8 bits. Because this is float, it's 8 bytes. Sorry. All right. So any questions, any errors when you tried it out? So in this tutorial, since this is an introduction, we'll be mostly be talking about single dimensions or two dimensions. It's a little bit confusing to visualize more dimensions than that, so we'll just keep the introduction to single dimension and two dimensions. But similar concepts extend to multidimensional. All right, so let's create a two-dimensional array. Two-dimensional array, you can think of it as a list of lists, and that's what I'm going to do. Array. Let me just type it out first. So I'm making a list of lists. And making an np.array out of it. So that's a, let's see, array underscore t dot shape. Got 2 rows and 3 columns. And the way to pull out a singular element from each of this is just by indexing it, how we index it like regularly. And let's say array of 0, array underscore t. So if I just say 0, it just brings out the 0th element. Notice that it's a complete array in itself. It's creating a new array here. So now from this, I can actually, if I want my 2 here, I can say 1. And I pull out my element by indexing it again and again. However, this is not the best way to do it. The easier the better way to do it is to just combine both of them with a comma in between them. It will be the same result. However, there is a difference here. This is slightly more performant when you have a larger array, because what this initial syntax is doing is it's creating this array, like an intermediate array first, and then indexing out of it. So when you have a large array, it's going to be inefficient. So comma within parentheses. This is not a usual thing in Python, but NumPy, it's very common. So we have range function in Python, and NumPy has a similar function called arange. And this creates an array for us, array range. In Python, we have range. Right, this range is basically counts from 0 till 1 before the ending number. So list is just the Python construct. So np.arange creates an array out of it. So array underscore f np.arange. So just a convenience function to create an array. Now we know how to index this array. Just your regular square brackets, and then the indexing counting starts from 0. And get the length of the array. underscore f, and the last element in this particular case will be 9, right? But this is true in Python also. You can start indexing from the end of the array using negative numbers. So array underscore f of -1 starts counting from the other side, not from the beginning, but the end. So negative numbers start counting from the end. So you can start indexing from behind. You can pretty much go so you can go count all the way from the back. Now, in slicing, I like to introduce slicing, and this is for pulling out portions of the array. So the syntax is basically your square brackets and then starting index, end index, and then step size. One important thing to note here, just like in the range function, you will get from start to end is not included. Okay, so end is not included. It stops one before the end. Okay, so if I want from the the 0th element to the 6th element, I need to give an end as 1. So for example, I have my array f, which is basically 0 to 9, and array of f from 0 to 7. And if I do not give the last step size is optional. If you do not give it, it's assumed to be 1. So this, it's called a slice. It's a slice of the array. You pull out a portion of it. Now the same thing, because my step size is defaults to 1, I can just do that, omit the 1. If I omit the start, it is basically 0. So I can omit the starting portion also, and I can just give the ending like that. If I omit the ending, that means it's till the end, till the very end. So by default, it starts at 0 and stops at end. This is probably not really useful. Sometimes it's useful because you can give a step size of -1 and actually reverse it. So this is a very common trick that is used. You use a step size of -1, so it goes in the reverse direction and reverse the array. The other trick that is commonly used is to get every other element. You can give it 2. So you start right at the beginning, you end at the end, but skip over every element. So count by 2s. Now if I want to just get the odd numbers here, I can skip the first element and then go till the end and count by 2s. So this is pretty much as the standard Python slicing. There isn't like too much different in NumPy. The thing that we need to keep in mind is that when you let's say I create another array out of this array underscore f. I'm just getting all the odd numbers out of f and putting it as array g. Okay. Now g is not separate from array underscore f. This is a very efficient operation because NumPy just gives a view of the data. It's not a copy of the data. So if I change one of these, to obviously array G changes, but not since I have created my array G as a slice of array F, that also changes. So you need to be careful about this. But it's desirable because it's very efficient. If you really want to have a copy, you can say, just taking the same thing. Array of all the odd numbers and then copy. Now if I change array H, $99, I'm changing it to 188. Okay, but then my array F doesn't change. It still is at 99. So especially when you're calling functions and all that with arrays, you need to sometimes be careful about these things. All right. So we do have a little exercise here. If I can get back to the right slide here. All right. So a little exercise for you to try. Let's take about five minutes. So basically we have the slice in red, which needs to be extracted. So you need to have create the array as in this command here, np.arange, which gives 0 to 24, and then we are reshaping it since it's arange gives a single dimension. We are just reshaping into 2 dimensions. I talked about slicing in a single dimension. I talked about indexing in 2 dimensions. So let's put those two together and basically have one expression to extract both, like the colors go together. So basically need an expression to have extract out all the reds here, another expression to extract out the blue squares here, and another expression to extract out the yellow. So just a clue here. NumPy dot range. Let's do this. So A is a 2-dimensional array, and the way to slice it in 2 dimensions is have comma, and basically here I have not given anything, so everything is default, so we get back the whole thing, and this is how you slice 2 dimensions. Okay, so so 2-dimensional indexing with a comma, and then we combine slices with them. So now the trick is to put together the numbers in the slice so that we get Only the red portions, that's one slice that I want. Only the blue portions, that's another slice that I want. And only the yellow portions, that's 3 slices. So let's go with the solution. So I already, let's do this. np.arange. Oh, I didn't give a number. Okay. So the mistake I did here is requires stop to be specified. So there is some error here. Let's say I don't know what it is. I can look at the documentation here and say, okay, it says start, stop, step. Things in square brackets, they are optional, but notice that the stop is not optional. So when I initially gave call the function like this, it didn't have a stop value, so that's why it errored out, and basically it's saying a range requires stop to be specified. So I believe the number is 10, not 25. So that's a single dimensional, let's say, let's just say a shape. So what reshape does is take this single dimensional one and make it 2-dimensional. So it becomes a 2-dimensional array. I'm just going to put it back in A so that we have what we need for the problem. All right. So this is the starting point. And let's say we get started with the red. Now, red is basically the complete first column and the complete third column, right? So let's do this. So I'll first try it out with a single row because my columns are the internal dimension. So I took out one row of the array, and basically I need to get the 1 and the 3. So when I'm slicing, I need it's the every odd index. So I'll start at a 1 and go till the end, but step over by 2 and is going to use the more efficient way of indexing, which is a comma. Now, this is basically pulling it out from the 0th row from here. But if I look at my figure, I want the complete row. I want all the rows. So what I do is use the slicing notation of just colon, which means give me all the rows. Start at the beginning and at the end. So just this colon as a shortcut for all of them. So that's my red one. Now, let's do the yellow one first. Yellow, that's the last row. That's probably easier. The last row is basically -1, and then I need all the columns in there. So I do that. I can even just do that because it's all the columns, the inner dimensions. It's kind of optional. So either a -1 or colon. Okay, now the blue ones. So this one is okay. I need in the first, okay, in the first row. Let's let me pull out the rows first, and the third row of. I'm just getting my two-dimensional indexing syntax ready. So the first row and the third row, we did that before, one till the end, and then we step over by two. So I have the first row and the third row, 5, 6, 8, 5, 6, 7, 8, 9. Let's see, I have that. 5, 6, 7, 8, 9, and 15, 16. Now I need to modify this so that I get the 0th column and the second column, which is again my, I start, notice that I don't take the fourth column, so I should stop before. So I start at the 0 and let's say second one. Now, I don't want to do this. I don't want to stop at the second one because it actually stops before that one. So it stops at 1. So if I do this, so this is 0th column, 1, and then a 2. So the intersections. I think I drew all over. So that's. Oh, I need to count by twos because I need to skip over them. I had it wrong earlier, so I had it like this, which is 5 and a 6, which is not what I want. I want a 5 and a 7. So I need to go till, I need to skip over the second one, but go till 3 because I need till 2. So now it's 5, 7, 15, 17. Any questions on this? All right. So now we talked about slices and assigning numbers also. So let me get back to uh, the single dimensional ones. A equal to np dot range. Let's say 10. Okay, so just so that we have more numbers. I'll just do 10 plus 5, just so that we don't confuse between indexes and the numbers itself. Now I can have slices here. Let's say I want to get all the odd elements. So I start from 1, go till the end, and I skip count by 2, right? So this is basically a view into the array underscore A. So we still have that data. Now this has 1, 2, 3, 4, 5 elements. I can even just assign to it array underscore A 2. I can assign, because this is 5 elements here, I can assign 5 numbers here, a list of length 5. Let's do a bigger number. So 40. So you have a view into the array, and then you pull out a slice. You can assign a list to it directly, but notice that since we have 5 elements, we need to actually assign 5 numbers, and it actually changes the original array. Now, if I try to assign, I made a mistake somewhere. Let's say I made a mistake and I had the wrong length. Could not, we have an error here saying that could not broadcast input array from shape 4 comma into shape 5 comma. What it is complaining about is that, hey, this one you have given, I can make it an array, but it's of size 4. And this one is actually of size 5. I cannot fit something of size 4 into a size 5. Now, I kind of lied when I said it has to be the equal length. It can also be 1, because 1, when you duplicate it, it can be made any size. So I can say 99 like that, and I put the same number everywhere. So 1, perfectly fine, or equal number. Now, I like earlier we mentioned about slices sharing the data actually. And so for example, if I create another array called B, which is a slice of the original array, it actually shares the same data, and changing B will change array A. B of, I don't know, it's 3 equal to 5. So I changed B, but since B is a slice of array A, even array A got changed. Now, sometimes the way to check is there is a function called shares memory in NumPy. Oh, sorry, not AB. My array A and a B. Right, sorry. So this is a handy check to see if modifying one will modify the other, because that happens quite often. Right. So we talked about slices. The syntax is basically start, stop, and then step. And this works if you have a very uniform way of going through the data. You're counting by 2s, or you're counting by 3s, or something of that. What if I have to pick out data which is in random locations? Okay. That is called fancy indexing. And there are 2 ways to do this. You can give the index numbers directly, or build a Boolean mask. All right, so first let array A, I'm just recreating at this. I want to do, all right, so give indexes directly. So one way to give indexes directly is array A, and you use the indexing syntax square brackets, but inside of this you give the indexes. So say, for example, I want the 7 here, which is of 0, 1, 2 index. Okay, so I need the second element, and then I'll take the 8, which is also the third element. I want the 12, which is 0, 1, 2, 3, 4, 5, 6, 7. And then I will take 0, 1, 2, 3, 4, 5, 6, 7, 8, 9th. I'll do the 8th, just so that it's not uniform. I just don't want it to be. So what I can do is, for the indexes, I can give a list directly, and I just get that subset of the array out. Again, 0 indexing. I can also index it from the end. So negative numbers count from the end of the array. So you can index it from the end side also.
Do those indexes have to be in order?
No, it can be out of order and you'll get the numbers out of the order. So for example, if I say -2 here, it can be any order. It can actually even be repeating, just what your need is. So here I have repeated 2 and 3 again. You get 2 and 3 again. Okay. And so this is really helpful if you have some other variable there, which is checking for something or doing some other operation and collecting all the indexes where you have something desired, and you can use it. So I can say index list equal to 1, 4, 2 minus 5, something like that. And I can say array A, and then just give the list directly. So you can do the indexes directly. Now, the other way of indexing, random indexing with booleans. So now what is a boolean? Boolean is basically a special kind of data type in Python that is it can only have 2 values. It's either a true or a false. Okay, so when you're checking something is like in your if loops and all, you have a condition, right? It's basically checking if it's something that is a true value or a false value. So what we can do is to index the array with true and false values, where the result will be only the values where the index is true. Let me so I'll demo it here. Array underscore a. Now I have bool index equal to okay, I need to have these many, so 1, so 10. Some criteria I have, I don't know. I'm coming up with this. Let's see if I have. Generally, we don't construct it by hand, so don't get scared about this. I'm just, let's see. I need it to be the same length, otherwise it's going to complain. I have one extra, so let me just delete this one. Okay. So the Boolean index here is basically true and false values, and I can use that to index, and I get only the values where I have truths. False values are ignored. Now, constructing this by hand is tedious and probably not, I mean, we don't have to do this. The most like good demonstration of where this is useful is using operators. So for example, I have my array underscore a with some numbers, right? I want to pull out only the numbers which are divisible by 3 underscore a. How do I know if something is divisible by 3 or not? I'll take a modulo operator. Okay, and a number is divisible by 3 only if the denominator remainder is 0. So now I here this is just a modulo operator, um, and it creates a new array for me with just the reminders, and array underscore a 3. Now I want to check if the remainder is 0 or not. How do we check if a number is equal to another one in Python? Double equal to and then a 0. Now this gives me Boolean values. Okay, now I can say div 3idx equal to this whole thing here. What this is essentially the operation that I'm doing, and I'm creating the array here and saving it in a variable called div3idx, right? Now I can say array and just get those values. So different ways of pulling out numbers from there. Any questions about what's happening here? Yes.
Is this directly related to the where function?
Yes, where also we do use booleans. So you can use, we will talk about where in a few slides. So this is called a Boolean mask. And short, I mean, we need not actually even have a variable there. We can just say this whole thing right there in the parentheses. Sorry, in the square brackets. And have the condition. Just one suggestion is not to make this too complicated. If it's too big, complicated, it might get readability or suffers. So if it's something straightforward like that, you can just put it in there. Now, fancy indexing in 2 dimensions. Okay, if I can find the slide. All right. So if we have a 2-dimensional array like this, and we can basically pull out random locations of that array, and the way to do it is again 2 dimensions, so we need to have 2 indexes here, and what the syntax is saying is you need to read both of these together. Okay, so take the element from 0th row and the first column, and then first row, second column, first row, second column, like that. Okay, it looks a little busy, but let's go over it step by step. All right, so A equal to, I'm just trying to construct that 6. Let's do this 25 dot ratio. All right. Okay, so we have a two-dimensional array here. So I want to pick up this 1 here, this 7 here, this 16 here. So I write down the rows which I want and then the columns. Okay. 1, 7, 16, and 23, right? So 1 is in row 0, and then column 1, and then 7 is in row 1, and column 2. So notice how I'm putting them in separately in two different variables. And then I'm not picking up anything from here. This one is, I want 16, so this is 0, 1, 2, 3. And then that's the first column. And then 23, 0, 1, 2, 3, 4. 23, 0, 1, 2, 3. Okay. So now I say A, and then rows, columns, and I just get those separately. So one way to verify it is to use a zip. And see that the pairs that we get out of zip is basically the indexes that we want for the two-dimensional array, so that uh, it's just verifying that, hey, I want 0, 1, the value from 0, 1, and the value from 0 to but for the array itself, you need to give them as two separate lists, the rows separately and the columns separately. Okay. All right, so time for another exercise, and we'll take a break after this. So let's take about 15 minutes, including the break. You can work on this, ask me any questions, or let's come back at this almost 2:55. So 3:10. Let's come back. Let's take a little break. Also, you can work, take a break, and we'll do this once we're back. All right, I'm just going to write down the indexes here because I can't remember anything. All right, so the rows that I need are 0, and then 1, 2, and then 3. 2 and 3 rows, and columns is 3, 1, 0, and then 4. I can use 4 or I can use -1. So since I've written them down on a piece of paper, I am recording it, so fine. All right, let me do the A again. Then p dot A range 5, 5, 8. All right, this is the original array. Yeah, that's in this figure. And I have taken note of what rows I want. 0, 1, 2, 3. Now columns equal to 3, 1, 0, 4. Then I just do pair them together so that I can just verify that those are actually in the order that I need them, because if they are out of order again, I'll get a different element, right? So anybody not familiar with the function zip? Okay. So this is only to verify that these are the actual elements that I need. A of rows, columns, 3, 6, 10, 19. 3, 6, 10, 19. Now, if I have any mistake here that my rows and columns are there out of order, I'll get a different answer. So for example, I made a mistake and I switched to a 1 here. Now, whatever I get out of my indexing is wrong. It will be in that particular order. And sometimes this can lead to hard to find bugs. So one suggestion is just, if you have a big array, start small. If you have 1,000 by 1,000 array, start small, maybe 5 by 5. Make sure that you are doing it right in that array and then extend that solution forward. So that's my fancy indexing. I think there is another question. Extract all the numbers divisible by 3 using a Boolean mask. So how do we find if something is divisible by 3? A modulo 3, it gives me the reminder. I have to check if it's actually equal to 0 or not. Then my Boolean mask is of true and false. Earlier we did it in a single dimension. This is in 2 dimensions. It can be any number of dimensions. And I can just use this as an expression within the square brackets, just copy pasting that here, and I get all the numbers that are divisible by 3. Any questions? All right. So moving on, we created an array using a range or just providing it with lists. Now we'll talk about more ways of creating arrays, because NumPy has a rich set of functions which we can use to create arrays. All right. And p.zeros, as the name suggests, it gives me an array of all zeros, and it takes a shape. So all NumPy arrays have shape. So I just say 3, it will give a single dimension with 3 elements. But if I want to give more than a single dimension, I need to put it in parentheses so that it becomes a tuple. So this is a 2-dimensional array because I have 2 dimensions here. I can create any n-dimensional that. So you give the shape that you need in the parentheses. So similar to that, I have once, some commonly used values, and we fill. So you can create an array, zeros and ones. There is an identity matrix, which you can do that. Identity matrices are like square matrices so that with the property that you multiply any matrix with that, and it gives back the same one. So np dot identity. Since it's always assumed to be a square matrix, it's only a single number. When doing this, notice that you have a one dot, which means that by default, this is giving me a floating point number. So for example, a and a dot b type. We have float 64. I do not know if it's the same on Windows. Windows might be different. So I can do np dot once, and I can give it a argument of d type, which gives which with which I can say what exact type I want. So for example, np dot once, and I'll do the same thing, 3, 5, and then d type equal to np dot int 32 in 64 int 8, whatever is needed. So I can force the type to be a certain thing. This is useful when, for example, when you know the characteristics of the array. Like for example, you're working with images. If you're working with images, either you have the values in an image from 0 to 1 or from 0 to 255. So that way you can optimize. You don't want to, if say for example, the images I'm reading is from 0 to 255, it's all unsigned integer values. I don't want to use a floating 64, which is probably the default, to save that array. And I can force it to be uint 8, so that I have a compact as just an array as needed, so that it's not too big. When you are working with too many images, such things become important. Larger arrays, remember that here we are using dummy examples like 5 by 5s and single dimensional arrays, but in reality you'll be using multiple dimensions and they're bigger, so sometimes these become critical. So we need to be careful about the d types. And also type coercion, like you cannot, if you have a array of type integers, if you put in a floating point value, it loses its decimal point. So those are the things that we need to keep in mind. All right, we talked about a range. A range is basically a sequence 0, 1, 2, 3, 4, but NumPy has other functions for distributions. There is a linspace. Basically, it gives a uniform distribution. So you can give it a start, stop. So for example, if I say, by default, it's giving me of size 100, np.lin space. So it's giving me 50 numbers by default. I thought it was 100, but it's actually 50. So I just gave it start and stop. and it assumed 50 points. So let's give 1 to a 10. I just want 5 values. Okay. Linearly uniform distribution. Similarly, there is log space. Signature is the same. What else? So you can also use random numbers, and they can be from a certain distribution. np dot random. There are two things with random distributions. There is an old style and a new style. I'll only talk about the new style. You may run into the old style, but it's basically np.random. They use directly, which is not recommended in the new usage. You need to actually create a generator, random number generator, np.random default RNG. And you need, and it's desirable that we give a seed, integers, and then size. So if you try this without the seed, you'll get another array. And the reason why we give a seed is to have reproducible results. So for example, when you try this just with our RNG equal to np.random and default RNG without anything in the parentheses, and you try this, you may get a different result from me. You might get a different result from your neighbor, and we will not have reproducible results. So typically, especially in demonstration code, we give something called a seed, a 0 or 100 or 42, whatever number it is. Okay, as long as it's a fixed number, we will have reproducible results. Like, however, if I every time I run this, you'll get the same result. So now if you run this, you'll get the exact same result as long as we are using the same version of NumPy. If I run it again, you'll get a different result, but this is reproducible across runs. So it's, especially in demonstration code, it's a good practice to have a seed so that you have the same thing again and again. Right? So if you have run this code with the same seed, you should pretty much get the same results. Otherwise, it means that either the NumPy version that I'm using versus you're using is different. Now, I just said rng.integers and 5. Again, this basically is, it's starting, if I give only a single number, it's going from 0 to 5. 5 is not included. So it's a low is included, high is not included. So low is inclusive, high is not inclusive. What else? Other kinds of distributions. Let me remove this. RNG.uniform, uniform distribution. And these are floating point numbers. Earlier was just integers, this is floating point numbers. So for this one, I can just give size. because the defaults are 0 and a 1, and I can give size. I get a uniform distribution. Similarly, that is standard other functions here. Let's see the documentation. I just need to give size. So a little exercise for us. One little correction here. This needs to be an open. There is a typo here. It needs to be like an, it's the endpoint is not included. So let's take about like 5-10 minutes. 5 minutes, I guess, to finish this up. So a few things I haven't talked about. I haven't mentioned np.py, but that's, you can just type it up in your terminal and see what np.py gives you. It's just a constant, your regular pi, 3.14 something something. And np.cos is basically your cosine function. Let's go over the solution. Generate 8 equally spaced points across the interval. If it's equally spaced, it's linear space between -10 and +10. And then we need how many points? 8 points. I have an error in my function call. Oh, num. Okay, I said size, it was actually num. So start is -10, 10.0, stop is 10.0, and num equal to 8. And then what do we need to do? Call this x. So x. Scale this data by pi divided by 10. So scaling is essentially multiplying x times. Oh, let's do np.pi. What does np.pi give us? The regular pi value, 3.14. I can, what do we want to do? Divided by 10. Divided by 10. So I need to scale this value, np.pi divided by 10. So take x and scale it as nothing but multiplying. So scale it and save that to x. So x equal to, so the whatever data was there previously was discarded. You have overwritten the x variable with the new values. So x, x is that thing, and np.cosine y equal to np.cosine. And like we talked, NumPy, that has a lot of mathematical functions which operate completely on the array, so we need not go through the headache of actually iterating one after the other. And that's it. All right. So NumPy also has capability to read um, text files. So the command is essentially np.loadText, and it has certain options, and we can use that to read files. So in general, it's useful to actually look at the text file first before trying to read. Um, let's see, in our exercises, there is a folder called load text, and there are different text files here, and float data.txt. So we'll try to read these files. Float data.txt, very simple, straightforward data. There isn't anything fancy going on here. So let's try to read this. The one thing to note is that when we specify the file, we need to give it the correct location, and sometimes defaults might trip you up. So what I typically do is, in Jupyter, I can do an ls, which means list the files here. Oh, and I shouldn't have a space. Okay. Percentage sign is what Jupyter notebooks call a magic function. So these are not part of Python per se, but they are very so useful that it's available through the Python interpreter, which is Jupyter. So ls basically lists all the files in here. So I need to get to the exercises and then load text, and I'm using tab completion here. And when I execute the file, it gives me all the files that are in here, and I want float data.txt. Like that. I do this so that it's a convenient way for me to check that the file actually exists, and now I can just copy paste it here. Now we saw the float data.txt. It's 1, 2, 3, 4, 5, 6, 7, 8. It's reading that file and interpreting it as a two-dimensional array. So I can save this. And this becomes a regular. In all array operations can be done. So there are other examples here which are a little bit more complex. They have a header. So for example, if we have, let's try to read this one. Float data with header. Okay. NP load text. Try to read this one. Okay. And I get an error. My big red blob Jupyter is angry with me. So what's happening here? So if I look at this file, right, it has characters in them. So it's not able to convert those characters into floating point values. And that's what it's saying, could not convert string to float, C1. Okay, so there are there are options here, like basically the arguments for load text. I can specify, let's look at the documentation, maybe that's it. Okay. So the D type, it's the defaults that have been, that it's assuming is that it's a float. So you can say, I don't want a float, I want a string. Okay. Or you can say, I can skip rows. So one thing I can do here is to say skip rows. Don't read my skip rows. Let's see where this is a little too big for me to read. So skip rows. What does my skip rows says? Yeah. Int optional. Skip the first skip rows lines, including comments. Default 0. So I need to say how many rows I want to skip from the top. So I need to skip the first. 0 is don't skip anything. 1 is skip 1. So then it's actually ignoring the first row here, because this one is the, basically it's the header in there, and we don't want to read it. It's not part of the array. It's some useful information, so we skip it and then read the rest of it into our array. So if I skip rows equal to 1, then it reads. So there is yet another file here, complex data text. So there you have to uh, ignore more lines here. This is all like mixed in together and stuff like that. So one thing we can notice here is percentage sign is being used as a comment in this particular file. So NumPy load text has an attribute called comments, which you can give the percentage sign, and basically it will ignore those. Okay, you can try that. All right. All right. So moving on. So we have been using, oh, actually, let's take a minute so that you can try the load text. Any questions, comments? Try to read this with comments. And the delimiter is also different here. It's a comma instead of a space. So let's see what load text assumes. Delimiter is none, so that means what are we getting? I can't read anything. String optional. Default is white space. So the character used to separate the values, the default is white space. The complex data has a comma, so you'll have to give the delimiter and the comment and skip rows. Oh, and there is a useless column here, so that's going to give trouble because this is not floating. Let's see if we have an option to skip columns. Use columns. There is a use columns.
It's like confusing.
Yeah, with different things like to, this data is not like extremely well formatted. Well, in some sense it is. For a human it is, but we need to tell it exactly what's going on. Like, ignore the first row, ignore the percentage signs, use a delimiter of a comma instead of a space, and then don't read that column. So multiple problems in one file. All right, so I'll try to do this. So if I just try a simple load text, it's basically complaining about dash dash. So it needs to skip this one. So the first thing I need to do is skip rows equal to 1. Now it's complaining about percentage sign, and percentage sign was used as a comment. So comment, try that, and then there is something else. Oh, what is the one? My argument itself is wrong. Oh, delimiter. Delimiter, no, no, the comment is different. I comments, yes, yeah. I had a typo there. So, and then there is something else. Could not convert string 01 comma to float. This is kind of misleading, but essentially, since the default delimiter is a space, it's trying to break on spaces, and then it gets 01 comma and it doesn't know what to do with it. That's what it's complaining about. So now I need to go back and add delimiter. So one thing to avoid typos is I can just say, for example, here delimiter and then do a tab. It will complete it for me. That way we can avoid typos. And then delimiter, I need to give the comma. Still more errors, and then could not convert string to float 80766 whatever it is. So I need to ignore this column, and to ignore columns, the thing is use columns. So I need to give it the use columns is probably a list. Yeah, int or sequence optional. So sequence is basically like a list. So I need to give it all the columns that I actually want to read. So complex. So I want 0, 1, 2, and then 4. So I have to give it. Let's use columns and then 0, 1, 2, 4, skip over 3, and now I get my array. So array, well, I don't want to name it complex. I don't want it confused. Okay, array from text equal to, and now, however I got this data, I have cleaned it up. I have a nice array. I can say, so array from text. There is something called numpy.save. This is pretty much the default way NumPy arrays are saved. And what we need to, it's, you don't, like once you get the data and you clean it up, do some operations on it and all, sometimes you would like to have a snapshot of that data. This is the primary use case for np.save. Its primary purpose is to save the NumPy array. And you need to give it a file. You can just give the name of a file. Okay, array from text, and then the second one is arr, which is the actual array that you want to save. So now if I do an array, it will be here. So it's saved with a .npy extension. That's basically a NumPy. It's an indicator for a NumPy array. And to load it, I need to use np.load. So a file, I need to give the first argument is file. So I need to say, I need to give the path to the file. So array from text.npy, and npy load. I'm just making up names here. So npy load array is here. So we can create NumPy arrays from text files, CSV files, all the other things. Also save NumPy arrays, like pure NumPy arrays. All right. So I would like to go over one of the main use cases for NumPy is calculations, and we'll just briefly touch upon a few things about computations with arrays. There are many more. So I would suggest going to the NumPy documentation and looking at what you need. Let's see. So some of the simple examples that we have done, equal to np.array, just very straightforward. I'm just creating very dummy arrays here. So when we are doing operations on NumPy arrays, we need to be cognizant of the dimensions of those arrays. Otherwise, we are going to get errors essentially, and we need to make sure that our dimensions are compatible. So, for example, I can array dot shape b dot shape, and these are exactly the same shape. So I can do a few things with this array underscore a plus array underscore b, simple addition, multiplication, stuff like that. A lot of the operations in NumPy are element by element. So you have, um, if an operation takes two arrays, one it take okay, first element from here, first element from here, do something with it. First element from here, first element here, do something with it. Okay. So whenever we try to do an operation, NumPy first checks for size compatibilities before doing that. So for example, let's say I have an array C, which is NP. So earlier it was it was 4 elements, right? Now I'll just do one with 3 elements. So if I try to add a plus, okay, it's basically complaining that you cannot add an array with 4 elements with an array with 3 elements. It doesn't know what to do. One thing we need to note is the terminology broadcast. Okay, keep this in mind. I'll come back to it. Now, however, I have an array. I can add a single value to it. Okay, so this one is 4 elements in it, the array A. I can add a single number to it. I can also do that. It's a list of a single element. I can also do an array. So it doesn't matter if it's a single element, if it's a list, or it's a NumPy array. What's special here? It's a single element. Okay, whenever it encounters something with a single element, it will repeat the same thing again and again. And that process is called broadcasting. So again, single elements are special. The other thing to note is some of the operations basically reduce the whole array. For example, sum. If I say sum, it just adds up all the numbers. So this is array underscore t, and I'm just making a 2-dimensional array. I made a 2-dimensional array. Oh, sorry, I wanted to do a shape. 4 rows, 6 columns. This one you can do a sum on it. What happens? It's adding up everything together. Okay. Now, for these kinds of functions, which there is also mean. Mean is basically your average. For these kinds of functions, you can also tell it which direction. If you want just like row by row or column by column, you can give options to it. And for that, we need to know how to number these axes. So NumPy arrays can be multidimensional, even though in this tutorial we are only talking maximum of 2 dimensions, but still it can be multidimensional. So you can tell along which direction you want that particular operation. If you don't tell it anything, it will do like a whole thing, compresses the whole thing together. So we need to know about directions, and there is a visual in the slides. Okay, now what you have here, this is your output of dot shape. Okay, that's what you get out of it. And this is like the visualization of the array itself. This is the axis number. Okay, let's ignore what's at the bottom. Let's not worry about it right now. I'll just talk about what's at the top. So single dimension, numbering starts at 0, axis is 0. Very straightforward. 2 dimensions, okay, you have rows, you have columns. As you keep adding dimensions, it keeps getting added to the what's this, left side. Okay, so this is the 0th dimension. Your rows are your 0th dimension. Your columns are the first axes. If you have a 3-dimensional data, your 0 dimension is actually like going into the page, like this one, and then your rows, and then your columns. And on it goes. So this is 4-dimensional data. I don't want to try to visualize it. It's so your axes, and then the reverse way. Negative direction, negative indexing goes from the opposite way. So let's just do a few examples with this so that it's a little bit more clearer. Okay. So we have a 2-dimensional array here, right? So if I do a array.sum, it adds up everything in this. Let's go d.sum. I can give it an argument x. Okay, I tried to get the documentation, but apparently not. np.sum. So it has an argument called axes, which tells along which axes, that either along rows or along columns. Do you want it along rows or along columns? So, oh, okay. So I made an error here. I did not give it what array I want to add it on. It's basically saying it's missing one required positional argument A, which is basically the array. I forgot to give it that array. So what is happening here? So axis 0, if we, for a two-dimensional array, so that is 1 and along columns is the 0. So try this. It's adding up 0 plus 6 plus 12 plus 18 is here. 1 plus 7 plus 13 plus 19 is here. Like that. It's going along the columns. Now if I do axis equal to 1, we'll do along the rows.
Question for Is there any performance difference between using like array d dot sum and then the axis inside there versus np dot sum? Or is that just
It probably depends on the implementation details, but most of them it should be one should call the other one. So np dot some functions are available only on np. Just trying to think. Yeah, for example, np dot cosine, right? It's only available on np, but it's not available on array underscore on the array itself. But some functions are available in both places. If it's available in on np, which is like on the library itself versus on the array as a method of the array, in most cases it's interchangeable. One will call the other. So the difference here is I called sum from the NumPy library itself, and here I'm calling the sum on the array as an array method. So here, if I call it as an array method, I need not specify array again. I can just give the arguments directly, and it will be the same. The thing was I was trying to get the documentation out and I couldn't get the documentation on this. If I just say array name dot sum, it was not giving me the documentation. So I switched over to np dot sum so that it gives me the documentation. There's something internally that's like one is giving a documentation on this one. So array underscore t, there is a product. Oh, there is a 0 in the array. And array underscore t, we have a minimum max. That's the maximum value. If we want to get along a certain axis, we can give. So you can have along rows or along columns. Similarly for mean, all right. So there are also functions called argmax and argmin. Sometimes we are not actually worried about the actual value, which is the minimum or maximum, but we want the location. Why is it 3? Oh, max. Sorry, I thought I was looking at min and I was like, okay, why is it not? And underscore a dot arg. Basically, arg max and arg min give the location where it's maximum or minimum. Now, this poses a problem. For example, is my array t dot shape. Okay, this is a two-dimensional case. Okay, array underscore t dot arg. So array underscore t min. So array underscore d is basically like this two-dimensional array, right? So when I say a min, I'm expecting a value. Fine, I got a 0. Perfectly fine. But when I'm asking for a location where my minimum value is, notice that I'm getting a single value out. This is because of how NumPy stores data internally. It's basically starting its counting from here and 0, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11. So it's giving me the flattened out position of the minimum value. But since I have a two-dimensional array, if I try to pull out the value, right, using this position, I can say min position equal to arg array p dot arg min underscore position. Min underscore position is 0, which is the first value here. But if I array underscore d, and then if I try to use that position to get back my value, I will not get back the value because this is a multi-dimensional array. Two-dimensional array in this case, but in true for multi-dimensions. So what this is doing is it's basically using 0 as an index, which pulls out my 0th row, and it's pulling out the whole thing. Okay, so we need to translate the 0 back into basically we need to get 0, 0 here because that's the first position, and the function to do that, it's called unravel index, and you need to give it the position that you get and what is the shape of the array that I need to translate it into. So I can say min underscore position and then array underscore d dot shape. So now I can get the actual index back and I can use this to actually get the location. So unravel index is the key. Okay, so this minimum maximum we can get where it is. The other thing is if we are looking for particular values, we can use where np.where. So for example, array underscore t, I am looking for the value 20. Oh, okay. So I need to give a value. Let me look at it. I need to give a condition which is a Boolean. So what mistake I did is basically array underscore d, which is not a condition. So the way I need to call this function is where with a condition. So condition, I get it with array underscore d equal to 20. I'm looking for np dot. Okay, so I'm looking where in my array is 20. So I need to give it a condition. And essentially, I am trying to figure out my Boolean here, Boolean mask. I with array underscore d equal to 20. If I just do this directly, I get a Boolean mask. And what where is trying to do is basically give me the location of the true values. So for example, if I have something which gives multiple true values, right? Greater than 20. Multiple true values. Now let's see what np.var gives. Oh, let's not go into multiple conditions at once. Let's do one thing. Okay, I'm looking for a place where I have a 20 value, and it is here, right? Now, what did I get here? There is a array of 3 and then array of 2. This is again using my rows and columns kind of syntax where, okay, this is the third row, 0, 1, 2, 3. Okay, equal to, sorry. Yeah, 0, 1, 2, 3, third row, and then second column, 0, 1, 2. So it's basically giving the row and the column values separately in two different arrays. So it's not giving me tuples again. This is very similar to what we saw in fancy indexing with indices, where you give your rows separately and your columns separately. They are not together like a tuple. Okay, so row column, and then I can say array underscore d row column and get back my 20. Now, there is another usage for where. We are giving here a condition. The first thing should be a Boolean matrix, and we can, here we are just getting the positions here. But there is another usage here which actually constructs another array for you based on the condition. So, for example, you can have two arrays, and say, hey, if it's this condition, pick up the element from this this array. If it's not true, pick it up from that array. An example for that, let's say I have positives, a range from 0 to 6. Positive numbers, 1, 2, 3, 4, 5, and then I can say negatives. So notice there is a negative here. It just takes a negative of the whole thing, element by element operation. So I have a mask. How many elements do I have? 5 elements. I'm just going to say, I'm going to construct this by hand. True, false, 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 true. So I constructed a Boolean mask. Notice that all the sizes should be the same. Otherwise, again, I'm going to be in trouble. np.where. Now I want to have a condition where I say, if I have a true value, take it from the positives. If I have a false value, take it from the negatives. So if I have a true value, I take it from the positive. If I have a false value, I take it from the negatives. So some condition which is basically selecting between two things. So notice that these arguments need not be matrices are not. Why do I keep confusing matrices? Arrays per se. I can have constants like that because it's a single dimension. Single dimension can work with pretty much any size array. It should work with any size array because it can basically be replicated. All right. So all right. Let's get to an exercise. We have been doing np.arrange and reshape, and then 2 stars is to the power, so everything is raised to the power of 2, and then compute these. Let's take a little bit longer break here, 15 minutes. You can walk around and actually even complete this. So let's come back at 4:45. Yeah, I don't know what happened. The screen stopped recording, so let's see. Hopefully, something is somewhere saved somewhere automatically. I don't know. We'll figure it out later. All right, 4:45. Let's get back to it. All right. So let's first create the array p dot range. So, and then to the power of square that. And what do we need? The maximum of each row. So if we try a dot max, if we don't give it any arguments, it gives just the maximum value of the complete array. And I can never ever remember which axis is which. I get very confused. So I always refer back to these slides here. Okay, rows, that one is my row, so that one is 1. All right, so a dot max is equal to 1. That's the maximum of each row. So 225, 81, 9, and then 64. Okay, 196. I'm not doubtful about NumPy's capabilities of finding out the max. I'm only doubtful about my capabilities of giving it a proper axis. So yeah, but uh, really I have a copy of this printed out and on my desk so that I know which axis is which. And I generally do images, so I am like, okay, color images will be three dimensional, but black and white is just 2 dimensional. So yeah, very handy. All right, so jokes apart. Okay, mean of each column. So a dot mean. Okay, since row says axis equal to 1, and I can say with confidence that axis equal to 0 is mean. Um, and then position of the overall minimum. Okay, so I can find the overall minimum, which is the 0, but I need the position. So positions we get with arc min. That is 15. If this is it's a 2-dimensional array, what is 15? I cannot use it back to index, so it's not the correct position. Well, it is correct, but it's not in a format that we want it to be. So we need to do unravel. So np dot unravel index a dot arc min, and then I also need to tell it what the shape of my array is so that it gives me row and column. I can use this back to index. Did anybody do it in some other way? Some other way? There are few other ways to do it. We talked about np.where, and basically I need to look for the minimum value. A equal to a dot arc then. Why is it empty? Oh, not argmin. Sorry, I just need to find the minimum value. Argmin is 15, so my logic is wrong. So if I say minimum, so that is 2 and a 3. So I look for the minimum value in the complete array. Another way to do it is a dot min. So basically find where the minimum position is along the row and along the column, because we need the column row position and the column position, right? So find where the minimum is in each direction. Find the minimum in each direction and okay, and then but this is the minimum along the rows for each row. So the minimum on this row is 100, and minimum on this one is a 16. This is a 0. Here it's a 9. Yeah. So what I'm doing is along each axis, I'm trying to figure out what the minimum is, and of those, figure out the position where the minimum is. So two-dimensional. Dot arc min. So this gives me in the rows direction. And now I do the same logic in the other direction. That gives me a 3. So 3 different ways of doing it. Any questions, comments? All right. So I'll touch upon a couple of other topics, and then we will do a more involved example. Uh, if anybody misses the ending part of it, everything is there in the repository that you have downloaded from. All these exercises are in Give It a Try, and there is a notebook here with all the solutions. So you can just look at the solutions here like that. There are bit more involved exercises which we have not done it in this class just for the sake of time. I hope to go through at least, well, we did load text. Okay, all the text files that we read earlier are here, and the solutions are also here in case in two formats. One is in Python file, one is in a notebook, whatever is convenient to you. We did this load text, all of them, but the solutions are there. And the rest of the exercises, you can see like the state, yeah, problem statement here at the top, and then it'll have a little bit of, this is a solution, sorry, I don't want to look at the solution yet, but if you look at the file which does not say solution, it will have like the problem description and a little bit of a starter code for you to practice NumPy and get a better feel. This PLT is basically matplotlib, which we are using only one or two commands of, basically to visualize uh, the NumPy array, because arrays are kind of large, right? It's not like 5 numbers which we can look at. So since this is kind of little bit non-trivial data, we need some plotting tool to look at it. So it's minimal amount of matplotlib here just to visualize it, but you have the starter code. So I just want to go touch upon a couple of topics before we end. We end at 5:30. So I'll touch upon a couple of topics and then do one of these examples, which gives a better feel on how NumPy is used and like for realistic problems. All right. So array broadcasting, just mentioned that this earlier. When we are doing array operations, we need to make sure that the array sizes are compatible for that particular operation. Uh, so for example, let's see, I'll just do this right. All right. A equal to np dot once. Yeah, let's do this. So we have a which is basically ones, and B, which is basically ones. Okay. Now, when we try to add these, right? So when we are adding two arrays, logically, like pure mathematically, it has to be of the same shape. But what is happening here? This still works, even though they are not of exactly the same shape. This is where NumPy is doing broadcasting, and it's trying to accommodate your function by using certain rules. Sometimes it will not be able to do it, and then we'll get an error, but there are some rules, and it works. So what is happening here? So here A is of what shape is this? A dot shape, 3 and 5, 3 rows, okay, 5 columns. What is B dot shape? 5 and a 1 on the other side. So what is happening here is when it's trying to add these two of different sizes, it's saying, hey, B is of shape 5 comma 1, so I can replicate that 3 more times, because that will make it compatible with A, and my operation can be done. So if B was of some other shape, right? For example, let me create a C. Let's say it was of 3, you know, this will not work, because the innermost dimension, it'll, okay, you have 1 here, right? It's of size 1, but then it cannot replicate 3 again and again, however many times. So it can replicate the 3's 3 times, say for example, to get 3 rows, but then you have the number of columns is 3. A has a number of columns of 5. So those are not compatible. That's what it's complaining about. Okay. So broadcast together 3 comma 5, which is my size array A, and C is 3 comma. It can work if it is 5, so that it can replicate it. Okay. So when you give an element of a single one, also it's the same thing, but since it's dimension 1, it can just replicate it however many times it wants. The advantage with broadcasting is a copy of the data is not made. It's just a view again and again. So you don't have a memory overhead of actually trying to construct such an array by yourself. If you hand construct it, you'll have you'll take up more memory. That's one thing. The other thing is changing of reshaping, right? So we have B here. We have done reshape. This is okay. Let's do this. This has 5 elements in here. I can make it vertical in the sense that 5 rows. So this is making it 2-dimensional, 1 row, 5 columns. I can also make it by adding new axes. Axes. So here I used reshape syntax. Here I added a new axis. So making a single dimensional one into a multiple dimensional one using this np.new axis. Colon basically means get all the rows. I just need it in a 2-dimensional way. This comes up most like when I first was learning about scikit-learn, um, the y, like the that needs to be of a certain shape. So you use reshape to manipulate that shape to be in a certain way. So that's where it comes. All right, this is just a pictorial representation of what is happening here. The first example basically is saying, okay, hey, you have a 4 by 3 array. You add it to a 4 by 3 array, which is, perfectly fine. This is just a repetition of this, the one on this side. So this and this are the same. So you get a result. Fine, I can add two matrices, two arrays of this same shape together, no problem. That's the first situation where I don't have a mismatch. Here in this case, what's happening is I have a 4 by 3, and this is 3 comma 1, right? So my one dimension gets stretched out however many times I want, and in this case I need a 3 additional times, and now I can add it. So that way it becomes 4 rows and 3 columns. In the last case, what is happening is that I have a like 4 rows and 1 column, and this is just 1 row 3 columns. So it gets stretched out in both of them are getting stretched out in these cases, and eventually we'll get an answer. So different ways of different conditions for broadcasting. Okay. Now, for example, here 4 by 3, here if it's a 3, it's fine. It can replicate this along the rows. Fine, make 4 rows out of it, and everything works. But if this was 4, right, in this case, it will not work because it tries to replicate it from the innermost thing. So it tries to see, okay, 3, is it matching here? No, it's not. So I'm trying to replicate it. But here it's not a 3, right? So it's not going to match it. So it's not going to work. So sometimes we need to be careful about these things. Bit more involved example, you can try it out. The main thing about broadcasting is that it's done without any memory overhead, very little minimal overhead, so you're not copying everything. So the other topic I wanted to touch upon is universal function methods. Lot of the operations in NumPy and the methods that are universal functions, ufunc, in other words, and basically you can apply them element by element or to the whole thing. So there are a few operators on it. So OP basically refers to the operators that are there in NumPy, and they have methods called reduce, accumulate, and outer and reduce at indices. Okay. Reduce basically takes the array and applies the operation again and again, each element at a time, so that till you get a single element. So for example, what is happening here is when I say array np.add is the function from that is already available, and if I say reduce, it starts and starts adding 1 plus 2, take the result and add it to the next element, which is the 3, then add the result to the 4. And this is an example for a string. We haven't really talked about string arrays, but you can actually even make a string array. Uh, Here is an example with logical and basically and works and or XOR. All these are logical operators. These logical operators work on Boolean values, which is our true and false. For example, the definition of and is the result is a true only if all my inputs are true. If any of the inputs is false, the result is a false. So here what's happening is, since this is a logical and, it is converting these values. See here, we didn't make a Boolean array, we just made an array of zeros and ones. By default, zero converts in a Boolean context, zero becomes a false, and one becomes a true. And that's what is happening here. True and a true, and a false and a true. There is a single false there, so the result is a false. The definition of logical OR is to the result is a true if any of the inputs is a true. So more than one, like at least one input is a true, so it's a true. Some more examples here. You can also do it along the axes, like you can say what axes, and equal, this is axis equal to 1. So if you say, you can basically constrain it according to axes. So reduce does that operation till we end up with a single value as a result. Accumulate starts and keeps doing it along the way. So for example, it's giving the intermediate values also. So for example, here we are doing np.add.accumulate. If we, in the earlier slide, it was dot reduce, where it added all the elements till it finally got one, the final sum. Accumulate is, it starts element by element. For every element, I'll give you the intermediate answer. So 1, add, that's the first, my first one, right? So that's the 1 here. 2, I take the previous result, add it to the element 2, I get a 3. Take that result, which is a 3, add it to 3, get a 6. Take that 6, add it to my next element, 4. So this is an accumulation function. So you have all the intermediate values. Reduce at, this is basically you're constraining where exactly you want your results to accumulate. So so reduce is everything, right? Everything is compressed. Your result is a single number. Accumulate is the result is the length of your input. Reduce at, you also give it indices like that, and it gives you the intermediate results at the desired positions. So indices here is 1 and a 4. So between 1 and a 4, sorry. So it's from 1 to 4. So 10, 20, and 30 together is a 60, and then the rest of it. It starts at your indices. All right. Outer function, it basically gives you pairs, everything. So this one, so here you have two arrays, one with 4 elements, one with 3 elements. So you have pairwise ordering for everything. So depending on the order of operations, you get, you know, this one plus this one. this one plus this one. So every element is added with every other element. So here you have 4 and a 3. So the result will be 4 times 3, that is 12. And depending on the order which you have done it, you'll get the results. Actually, there are many more functions. So this is just a sampling of what things can be done. Please go to NumPy documentation, numpy.org, to actually see what are all implemented there. This is the array data structure. This is what makes some of the things work, and understanding this makes some things make more sense. So a NumPy array is essentially a Python object, right? If you're familiar with object-oriented programming, and every object has certain attributes and methods, and these are some of the attributes on it. Okay, we talked about d type, the data type, and we have the number of dimensions, the shape, and then the strides. Strides is basically what NumPy uses internally to access the data. When you are indexing it, it uses the strides information to access the correct one. So the key point here is data. If you have like array underscore a, if you do a dot data, it will dump out everything, but it doesn't have any shape anymore. It's just one contiguous line of things. The indexing comes, like for example, if we have a two-dimensional array, right? The indexing where you specify the row and the column number, it comes from the strides. So the data itself, it's internally, it's stored as a single block. It doesn't have that rectangular shape, it's a line. And that's why when we do our min and our max, we get the position of it, which you have to again translate it back into this particular shape. Now, why is this important? Uh, this is important because there are certain operations which you do which are more efficient because the data does not need to be copied over. Remember, we try to use NumPys for like larger arrays and stuff like that, so efficiency is paramount. And when we do slicing, for example, right, we have a starting point, we have an ending point, we have a step size. And if we do a slice, if I have say b equal to a, and then I do a slice on a, b is not a copy of a. So b is just a view into a. What is happening internally here is that it's creating this part of it again. It's changing the strides basically because it knows the step size and the pattern where it needs to start and where it needs to stop. But the data, it's pointing to the original A. Okay, so the data is not copied over. So if you have like 10,000 elements in there, it's only one set of 10,000 elements, and that gives the efficiency. But something we need to keep in mind that, we change things if we mess with one. Now, if we do fancy indexing, where we give the actual positions where we want or the mask that we want, there is no logic to it, right? It cannot just change the strides accordingly and just index it there. It will have to save the whole Boolean mask or the list of what your indices are. So fancy indexing actually creates a copy of the data. Slicing creates a view. So that's not the only functions that have this difference, but there are many other functions that probably have that difference. So sometimes you'll get a warning saying that, you're trying to do an operation on a slice instead of a copy and stuff like that. And that's what it's trying to complain to you about. Hey, you're trying to change a view, but that may not be what you want to do. It's trying to be helpful. Sometimes you have to just pay attention to it and ignore it, maybe sometimes, depending on the usage. So that's what this is. So what this also means is that when we do a reshape, it can just change the strides and not create a copy of the array again. So reshaping, doing a transpose of an array, some of these things, they are very efficient because there is no copy of the data. And there are few examples of this. So that's all I have with respect to slides. I would like to go over a little bit more involved example, but couple of things I would like to mention if anybody wants to leave early, is when you're using NumPy, right? Try as much as possible not to have loops. If you have loops on your NumPy, you can index it one after another just like a regular list of lists or anything. But if you have a loop, you are basically not getting the power of NumPy. And be careful about your slicing and all that stuff. Slicing is a very powerful tool. Copying, make sure that your as much as possible you vectorize things. Vectorizing is basically using the NumPy functionality to do what is needed. You can add two two arrays by yourself, but you wouldn't want to do that. You would want to use the NumPy functionality. So with that said, if there are any, actually, you know what, I'll first take questions before going through any example. I would like to go over one of the examples, but first questions. We have only 10 minutes.
The data gives you a memory view. There's nothing you can do with that, right? Just the memory address.
Yes, so I can say b dot, not that, data. It just gives you a memory location and nothing. I don't know if you can override it by some voodoo, but I don't know that voodoo. So let's not mess with it. So okay. If there are no other questions, I would like to go over this one. I'll be uploading this notebook with all the random stuff in there onto the GitHub page, just so that it's there for reference. I don't know if we have the recording of the previous part or not. My recording stopped somewhere. So yeah, I will figure it out later. Okay, so an image is nothing but a NumPy array. So this is the image that is given to us. And what this exercise is asking us to do is essentially an image is a NumPy array. It's a array with along rows and columns, and each value there is the pixel intensity. This is a black and white picture. If it's a color image, you'll have RGB values, which makes it a 3-dimensional array. But here we are just worried about 2 dimensions. It's a black and white. So here, what we are asked to do is to do an averaging filter over it. There are libraries like scikit-image or sklearn-image and all that, which have these built in and probably are much better. but this is going to be a NumPy demonstration, so we are going to use NumPy directly for this. And the thing is, for every location, you need to take the neighbors of it. So the top neighbor, the right, and the left, and the bottom neighbor, and replace that value with the average of those 5 values, including this particular location. So that's what it's trying to ask. No, I need to put it. So this is basically showing that image. Plot.imread. Imread is available through a lot of libraries, and Matplotlib is one of them. NumPy, as far as I know, it doesn't have a direct way to read images. You have to use either Matplotlib or scikit-image or um, OpenCV or one of those other image processing libraries to get the NumPy array. Sometimes those libraries create some sort of metadata and stuff like that. So eventually, like, bottom line, all these libraries will read image into a NumPy array. Okay, it's just a matter of looking at that library's documentation to see where exactly the thing is. Okay, so I'll just go over the solution directly. We don't have much time. And so if you look at this, this is the operation. Eventually, we are taking a single pixel. Every location, every entry into that array is a pixel. That's the way the image is read. So you have, for every pixel, you need to take the value of the top one, the right one, the left one, bottom one, and add all 5 of them together and divide it by 5. Okay, and you can do each one of them in a loop. There is a solution here, but that's not the right way to do it. You'll get an answer, you'll get the perfectly correct answer, but that's not using NumPy. And here we are using slicing so that we get, okay, hey, I need, when I take an average of the 5, the right, this is my left, the leftmost one and the rightmost one and the topmost one and the bottommost one are cut out. So I'm just getting the middle part of it. And when I want the top part of it, I just, from the bottom, I just ignore the last row. And then at the bottom, also you ignore the top and just, like, imagine those to be like overlapping squares. Okay, eventually when you take an average, you are losing the border information because we are averaging it out. So we basically have to take overlapping squares and just add them all together like this. So I would suggest to at least look at this example. I find it super cool. There are other examples here in the exercises, and all of them have solutions. So any questions? I just want to stop here right now. I don't want to talk anymore. Any like in your work or anything, do you see using NumPy, or do you see it as a building block for learning other libraries? Definitely pandas is built upon NumPy. All your machine learning algorithms, they use NumPy quite a bit.
Is there a way to vectorize a custom function?
So first of all, the custom function needs to be so there are a couple of ways of doing it. One thing is you can say, hey, apply this function to everything. You can write the function itself in CPython using CPython API and do it. So the NumPy has certain functions here using NumPy C API, writing an extension module here where you can do your own custom functions, writing your own U function also. So this is a little bit more, but NumPy, the number of functions is just a lot. It has a lot of linear algebra functions.
Last year there was a presentation talking about a possible new type in NumPy
Oh,
called the units, maybe for managing units. And I'm not sure if that project is still going on or if you have more information on that, because it seems promising, especially for practically scientific computing, physical quantity.
yeah. I would look at this. So basically, what I did is a search for D types. I'm not part of the NumPy development, core development or anything, so I don't have any special insight into the latest features. So I don't see it here. Yeah. Maybe we can look at the GitHub page and I don't know if that's. They have 174 pull requests in there, so I don't know if. Yeah, I don't have any other insight. Yeah. All right. Thank you so much. I'll be here if you have any more questions or anything. I hope this was helpful. And please look at the exercises. They're nice. Thank you. You've been a great audience. Thank you.